Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure to host Professor Tong Zhang from Rutgers University. Tong has received a BA in Mathematics and Computer Science from Cornell University in 1994, and also a PhD degree in Computer Science from Stanford University in 1998. And after graduation, he worked in IBM Watson Research Center and also Yahoo Research Labs in New York City. And now he's a professor in Rutgers University in the Statistics Department, and his research interest including machine learning and algorithms for statistical computation, and also the mathematical analysis and applications. Tong will stay here for a couple of days. His office is just next to mine, so if you want to meet Tong, just send me an email. Today he will talk about greedy and local search algorithms for sparsity constraint optimization.
Okay, thanks for the introduction. So today I want to talk mostly about some more theoretical stuffs in machine learning optimization. So here's the motivation. So basically from machine learning, people are interested in the learning problem with a large number of features. Then if you don't do anything with that, usually you will have this problem called overfitting. So what people do is assume some structure of your target. One structure is sparse. Basically means that your target is a linear combination of a small number of features. In that sense, then you can form the learning problem as sparsity constraint optimization, which we'll show a little bit later. Generally, the problem of this optimization is it's an NP-hard problem. So people has to do the approximation algorithms. This talk particularly, we want to talk about a greedy algorithm. Essentially, this is probably a little bit dry in the sense it's more theoretical. I'll talk about variation of this greedy algorithm in the context of sparse constraint optimization, variations of greedy algorithm, and focus on the theoretical analysis. I know there are people in the computer theory literature also doing greedy algorithm analysis. They have different assumptions, basically submodularity, which not quite the same as the sparsity. It's not submodular. Actually, I briefly look. I'm not that familiar with this, but I really briefly look a little bit. I think the sparsity, you need a little bit more involved techniques than the computer literature type of greedy algorithm, because something you have to prove here, that's almost already given. If you have already assumed submodularity, you are already given something which you actually keys to prove something like something similar assumption of that, although it doesn't hold. Anyway, so here is the sparsity constraint optimization. The formulation is you want to minimize some loss function, which we will do the convex loss for now. So you have a parameter W, and then you have subject to W sparse. Sparse means the number of non-zeros in W is smaller than something, let's say K. Example is a logistic regression for binary classification. Basically, the loss function is log likelihood, negative log likelihood, actually. It's a QW. With observed data, this is training data, this is a negative log likelihood. You want to minimize negative log likelihood in the logistic regression, and then you subject to the sparse constraint. It's a L0 constraint. So that's the setup for the sparsity constraint optimization. The question is how to solve that. Generally, there are two types of strategies. One is convex relaxation, and the other is greedy algorithms. So in convex relaxation, the standard relaxation is to minimize this one, say the logistic or other convex loss, and subjects to, instead of L0 constraints, now become L1 constraints. The questions to ask in this context is what kind of conditions which will solving 2 can be approximate solution of 1. So you want to establish kind of, this is kind of a theoretical questions to ask and to study. The other approach, which is more of this talk, is about greedy algorithm. Basic greedy algorithm, we try to find the non-zero coefficients of W. W has a small set of non-zeros, one by one, greedily. So this talk, we will talk a little bit about the history and some variations of greedy algorithm in this context. Particularly, I will emphasize the theoretical aspect, so I don't show really a lot of examples. And also, I focus on my own research. There are a lot of other people doing this, so don't be offended if you find that I only mention my own, because this is really about, but I give a rough picture, but I probably don't give a very complex, comprehensive list of other people's, but that's mainly because this is my talk. So the type of greedy algorithm, one thing, I want to talk a little bit about that, because we want to say there are different variations, and this involves different ways to say what kind of greedy algorithm you are doing. One is you can doing loss function. A lot of people in the signal processing community doing this kind of least squares loss. In the signal processing, it's called matching pursuit. General loss function in the machine learning is called boosting. So people can classify by using loss function. The simpler is the least squares, and boosting is more complicated. The other thing you can do that is using the regularization. The traditional analysis actually have a L1 constraint. I will show why, give you some results to derive the theoretical results, including L1 constraints. Now you can also say you don't include the L1 constraints, and what happens. The third is optimization within the active set. Basically, you select the features, whether you want to do a full optimization within that set or not. It's non-corrective versus fully corrective. Again, there are some theoretical differences. That's also part I will explain. Then the last one, you can say the search criterion. Basically, the traditional greedy algorithm is forward. The local search, what I call local search, would be forward backward. Basically, you try to find a fixed point using forward backward procedure instead of strictly forward greedy. So you can view greedy differently by using this kind of different ways. There are also extensions. Particularly, I will talk about this extension. Basically, it has a generalization of structure sparsity optimization. You have a more general form of optimization procedure. Nonlinear, in fact, the boosting you can really, although I talk about linear, but you can easily do that nonlinear. It's not a big issue. So it's not even an extension. You just need to arrange your algorithm carefully. Even though this is in the context of linear. So related, again, I say the greedy algorithm in theory, it's a different assumptions. So this one is kind of different. History, mainly I would emphasize this theoretical analysis. I talk about different ways to look at the greedy algorithm, basic different variations, depending on how do you want to classify that. So one is with L1 constraints. L1 constraints, instead of minimize QW subject to this, I will minimize QW subject to also W's one norm is small. Not only W sparsity is small, but also one norm. This has been studied back, and then rediscovered here in 92. And this has a lot of impact because most modern work, actually this got forgotten, I think, especially probably in optimization. And this work mainly is brought up by Clarkson. 92 is a lot of people follow up. And there are other works. That's why I'm saying I'm not giving a comprehensive listing. But this talk I've read because I want to talk a little bit about my analysis in this one. So that's a slightly different than the original. This one is a variation. But when I did that, I didn't realize I don't know this work. I'm only more focused on extension of these guys. Then there's a survey paper. He said that there are long history. Least squares without L1 constraint is using least squares Q. W becomes least squares solution. And then you don't have this one. You remove this L1 constraint, and you just say sparsity constraint. This one is in the signal processing. It's a matching pursuit. This is not me, so this is a different John. So and they have some convergence analysis, but not rate of convergence. I will comment on that. And once you put instead of matching orthogonal matching pursuit, you can get rate of convergence, not only just convergence. I will say a little bit more about that when I talk about the result. And then there's in the signal recovery community, CHOP does some kind of feature selection. So I also did something feature selection with stochastic noise. It's a little bit extension of this work, but I'm not going to talk about any of these. I will talk a little bit about not in the least square setting, but in the more general setting. Yeah.
So convergence analysis. This is a non-convex problem, right?
It's non-convex. Yeah.
So it's convergence to a local analysis.
Actually, the convergence is to say that when you get k goes to infinity, then you have this convergence is when your k gets to infinity, you will find the solution of this. Even x can be infinity dictionary size.
So if k goes to infinity, that's no longer that is a convex problem. Is that constraint doesn't matter?
It's not. It's not. So I will talk about it later when we will show the analysis. In fact, you want to say what is the size of k. Eventually, here you want to say what k can be. Basically, okay. The result like this is. If I solve k, I cannot solve k, right? The type of result is I will replace k by k prime. K prime is a little bit larger. So complexity is a little bit larger. But then I can get as good this arrow as k. So you can define optimal k as this objective arrow. Then I will replace k by k prime. So that's a flavor of analysis. I will show you later, and then that makes more sense. Right, but of course, if you just play with it itself, you will get just say local. But no, this is all global. The analysis. The point is you don't want the local converge to local, so you have to change the style a little bit. But that's a good question. So we will see later the details. Here is the general loss function. So I will talk a little bit about these three. Sparse solution of minimize of a general convex, which is more in the setting of boosting. The original boosting, of course, is ADA boost with exponential loss, which they have a weak learning assumption. And the convergence, again, convergence is really say k goes to infinity, then you can converge. And Friedman has a different set of boosting without analysis. So we did some analysis more in this setting. It's convergence analysis. Because, by the way, why it's not, this guy gives the rate of convergence, but using the fully corrective boosting. You cannot use this one to get this kind of result. So this result, you have to, I will explain that later to get the rate. The rate is the more interesting one. And this one also shows that if you do the fully corrective boosting, you can also get a sparse recovery instead of with additional assumptions. So this is more to do with compressed sensing type of thing. So local search then instead of, again, you find the same problem. So this kind of same problem, but you really target with k. Now, you try to use forward-backward ideas, and we will talk about two variations. One is this guy, one is this guy. Basically, once you get that, you get a little bit better result. It have a better feature selection properties. We will see the what it means. Look at the results. And this also related to something away steps in the theory literature, CS theory literature, or optimization literature in the Frank-Wolf algorithm. That's with L1 constraint. Here we don't do L1 constraints. Okay, so the other thing is you want to do a little bit more general. So this is a QW versus sparsity. Now replace sparsity by a general cost function. This is structured sparsity instead of just the L0 norm, but you look at the support, just the set itself. You define function with respect to set. And then there are some results about greedy algorithm extension to this problem. And there are other extensions which are different. Like eigenvalue problem, there are something here, Q may not be convex, so you have to do that specially. Anyway, so I will look at, just give you a flavor of what kind of algorithm, what kind of analysis produces. So here is the L1 constraint. What it does is the following. Opt is actually just L1. So you remove this K now. What in K is, in this case, it's not L1 constraint, but K is infinity. But when you produce solution to this, you have a sparse approximation of this algorithm. And a sparse approximation with K-sparse, which essentially is this algorithm. Algorithm, each time you do a shrinkage of your current W, and you add one additional component. The additional component is greedily optimize your cost function. And then you update by adding these additional components, W. So each time you add one more features. When you have K steps, you have K-sparse W. Here is what you get with this kind of algorithm. Basically, this one is a unconstrained problem plus C A squared over K. You can make a constraint. It doesn't make much difference simply because optimal K or K prime is always smaller than OPT. So therefore, you can approximately solve this problem using, with a sparse solution. So this is type of flavor of that. Of course, it doesn't directly solve original problem. That's one thing. The other thing is main thing from algorithm point of view. If you want to implement that, say if you want to implement it to your learning algorithm, the main issue is really relies on A and also this eta. Eta you have to choose. This is a disadvantage. The proof idea, I think I'll briefly mention. So briefly mention in case there are some people doing theory here. So roughly you need to prove something like that. First, for each step from Wj minus 1 to Wj, you get bound like that. Basically, Qwj minus the optimal. This is your excess risk minus this guy square. And this one is smaller than. So this is your risk after another step, at the J step of a greedy algorithm. This is type of result you get. Once you get this result, you just solve this recursive relationship. The relationship that with submodularity, this is not submodular, but you have similar equations. Submodular is definition. It's definition of some actually stronger equation than this one. Basically, you Wj smaller than Qj minus something. There's no square here and something like that. So CS, this is actually what you really need to prove in the sparsity setting, while in the lot of submodularity functions, you assume that. And this is actually the key part, not the other part. Yeah.
So the Q's here are risks, right?
So right, risks.
They're averaged over some distribution, some assumed distribution of the test, of the data. They're not just training risks.
This is a training. It's actually just training risks.
It's in the check.
Yeah. Like the logistic regression. This is all talking about training. So I'm not talking about generalization.
Oh, this is just training?
Yeah. This is optimization. How do you optimize the training error? Yeah, completely say optimizing training error. There's nothing to do with generalization. Generalization is when you have a sparsity, you can get good generalization. So that's where it extends. That's why you want a sparse. here you say if you have some sparse solution, you can get some good generalization. Yeah.
Do you need the assumption of the objective is convex? Do you need any smoothness assumption on objective?
Yes, you need this one I didn't say. Yeah, yes, this is C prime. C prime depends on smoothness. Depends on kind of smooth. If you have, actually this one even assumes your derivative is Lipschitz. If derivative is not Lipschitz, only itself is Lipschitz, not derivative, then you have actually worse. You have square root of k. You can derive something. Yeah.
So this also any training set?
Yeah. It just depends on the smoothness of Q, but that's it does depend on that. Yeah. Right. Yeah. It holds on any training data. Generally, it's okay. Like logistic regression, it's smooth, so it's fine. Any training data, this holds, and this constant really is just the real constant. Once you get this, for example, logistic loss, maybe 1 or 2, whatever, something. But roughly, this is type of result. The key from algorithm point of view, I'm trying to say is you depend on A. It's not nice because you have many tuning parameters. One is K, one is A. Usually you want to tune 1 parameter. 2 parameters is okay, but there are other issues. When you really implement, I haven't seen. Basically, you can implement let's say boosting using this, but I haven't seen anybody really try that, mainly because it's just complex. The actually boosting algorithm tried is more like this kind of flavor. So you get rid of this L1 constraint. Here is the algorithm, basically without L1 constraints. With small step size, this is a little bit of variation of Friedman's boosting. Friedman's is this gradient boosting. This is you can do gradient boosting. This analysis also holds. Essentially, you don't get A. Now you're just adding 1, so you don't have shrinkage over W. That makes things a lot easier. Here you shrink W, you add A. You're doing you have A. Here you just don't shrink, you're just adding something. And then there's some theory, again, it's just so far this theory, as I said, is just convergence itself. The convergence is not trivial in the sense this dictionary can be infinity, very, very large. The convergence rate itself doesn't depend on the size of the dictionary. So that's why it's not a trivial result. It's just as you cannot avoid it. It's not completely clear. So you have to really prove that. The key is all this result doesn't depend on the size of theory, the size of the dictionary. Drawback is you have to pick the learning rate. And I cannot develop a convergence rate. Then you have to make another modification, which is a fully correct boosting to get this. So here is a fully corrective boosting. You just do this one. You can do the original one, or you can do the gradient. It doesn't make much difference. Just pick the largest gradient, or pick the largest components, which give you the most decrease of your loss. It doesn't change the analysis. The key is you have to do this. Once you find the active set, you add 1 element to your active set, you need to do a full optimization. This one is not does not exist, for example, in the adder boost or in the gradient boosting, and that actually makes a difference in the theory. Once you do that, then you get a little bit better, and you can also get a sparse recovery. So I will talk about sparse, but essentially, you get a flavor of this type of results. You minimize this guy, it's adaptive for all W, but it's with respect to L1 norm over K. And the key is if you look at the original L1 constraint, it's not adaptive to K. You have to know A and get a similar result. And here you get a similar result, but you don't need to know A once you do this optimization. And you get a freely adaptive A, and you don't have a learning rate. Here you also have a small step size learning rate constraints, even in the earlier. So here you don't need to get that, and you get a convergence rate.
So,
yeah.
At each round you ignore the previous weights, but you just find out the working set and then you relearn the weights.
Yeah, that's exactly, yeah. So that's a fully corrective. And then you get adaptive results. This one I haven't talked about the backward step. So next one will be backward. But the main thing is to observe this is good, but when you do the sparse recovery, it's not necessarily optimal. You can do better when you have the backward step, mainly because I will talk about a little bit later. The proof idea roughly, basically you get a similar equation as what you get previously in the, but this one it doesn't depend on A. Instead of depending on A, in the setting of here, the L1 constraint, you depend on the any target. This target can be anything, which is has to be k-sparse, and you get this, and then you get something like that. Sparse recovery. So sparse recovery, you can use this fully greedy algorithm to do sparse recovery, which is more targeted to the sparsity constraint. This one is loosely to do with sparsity constraint because it have L1 regularization here. But a sparse recovery, you say you don't have L1, you have L0. Roughly is the following. You have a little bit stronger assumption. I don't want to talk about this assumption, but this one make more sense in compressed sensing than learning. So k-sparse signal, basically L0 is small, and also you have to add a condition, this guy is small. The reason is meaning that this one is close to a global optimal. Derivative of a target is small, that one doesn't appear in the earlier. In this kind of result, you don't need to assume that. So you need to add especially these two assumptions. Once you add that, you can say recover the sparsity using this algorithm, fully corrective. Roughly to say you have, once you find k is a little bit larger than k bar, the original sparse, you have to do step more than k bar steps in order to get this kind of results. But then it's not too much larger, it's constant larger than the k bar. Then you get this flavor. Basically, wk minus w will be smaller than, it doesn't depend on k, but it depends on k bar epsilon. Oh, actually, this should be O. I'm too optimistic. There should be have a big O here. And once you do that, you get recover. For example, if epsilon is 0, basically means that if your target is sparse and is a global solution of the unconstrained problem, then you can recover W bar exactly by using greedy algorithm. So that's kind of flavor results. But slightly suboptimal in the feature selection. I will briefly say how do you do that. Roughly, you get a stronger, you have to first do a stronger type of, this is always a key, one-step progress. You have a wj minus 1 to wj. You say how much your each greedy steps decrease your objective function. And you roughly, you get a stronger results than what's by using under this assumption. Under this assumption, you can get stronger results. And then you manipulate a little bit to say this set decrease. Either this set will decrease or this is small enough. So basically, you say once you get this guy, either this is sufficiently small or this one goes to 0. So 2 has to happen. But if this goes to 0, you already recovered the original sparse signal. So that's a rough proof idea. Another thing I mentioned, you can improve that using local search. Here is a local search. Again, now this one is real sparsity constraint algorithm. The local search algorithm, I define optimal k. K is to say the minimum of what you can achieve using the Q of W with the sparsity k. The best you can do with the k-sparse target. So that's optimization problem in terms of k. Then with some fixed k, what I do is the following for the local search. Repeat the following steps until decrease of Q is no more than epsilon, for example. Basically, you add one feature. At any, you're starting with an arbitrary set of k features. Then you add one feature, make it a k plus 1 sparse vector. This one using the fully corrective boosting. You do one step, then you fully correct it. And then you remove one feature from that. After that, you from k plus 1 feature to k features. You remove that with the smallest this one, or with the smallest decrease of your Q. Either way is fine. But roughly, you add one and remove one. You just keep doing these two steps. So this is a local search replacement strategy. Once you do that, you get this kind of result. Again, under some kind of strong convexity, you can say, I can find QW smaller than optimal K bar plus O epsilon. Epsilon is in the algorithm. You can set epsilon to be 0. You let it goes to 0. It just affects the speed of the algorithm, but not the result itself. So you can think about epsilon to be 0 effectively. You want to compete with some optimal of K bar using a sparsity W of K. Here, algorithm is W is K. Then you want to compete with K bar. So how good you can compete with K bar? K bar you have to do smaller than C of that. That depends on your condition of loss function. Basically, it's a constant within 0 to 1. So essentially, you are saying, I cannot solve the original K bar problem, but I can solve a little bit worse problem with a little bit larger complexity. That complexity K is at least constantly larger than this K bar sparse solution. So that's the flavor of this result. So indeed, you still cannot solve this optimal K bar within the itself constraint, but you can solve that with a little bit relaxed constraint. So that's actually to do with your question. So yeah, this kind of flavor, yeah. And it's a global optimal. It's compared with global, yeah. So suboptimal feature selection for sparse signal, basically K always larger than K prime and cannot be reduced, at least in this style analysis. You do a little bit of proof idea, just the high level idea. You see how it goes. You add one feature. Again, you add one feature. You want to say how much is the decrease. The decrease you can say is at least this for some C1. Remove feature. This one gets increases, not improves. It should be increases by at most this guy for some C2. Then you solve that. This one, if you make progress, if this one is larger than this one, because you decrease more each step, you're adding less. And then you slide to a manipulation, and then you just say, and this one is larger than this guy, when this one is smaller than this one. So once this holds, your decrease is always increased than that, unless this one is minus, starting to be minus. Okay, so therefore you just keep doing until you get this kind of thing. So that's rough idea. But then you just go to details. This high level idea. So more aggressive local search. It's actually earlier than that paper, but it's more targeted for feature selection. You try to minimize this L0 of this form, and you define the local condition. Basically, two-step local condition to remove to reduce this L0 regularized objective function. One is addition. Addition forward, you W decrease. This guy increase by lambda. You're adding one feature. This one will increase by lambda. This one will decrease. Feature deletion. This one guy increases, and this one will be decreased by lambda. Idea you want to alternatingly adding, deleting to reduce objective. It's have this kind of flavor, except it's kind of this flavor algorithm, except this one is hard constraint, the other is soft constraint. But then in addition, if you do soft constraint, there's another idea you have to do is a track sparse solution. This one has been around in the statistics literature, turns out to be effective. You're starting with lambda large, then gradually decrease lambda. And that also has to be done. And you cannot with a very small lambda, because if you do very small lambda, this guy L0 quickly increase until you're starting to backward step, which is not good. So you have to start with very large, then gradually decrease. So you combine these two ideas, you get this kind of algorithm. You have a forward step error reduction. You're adding one feature. Then you check if it's small. If small, then you are done. you have backward. You have a backward step. You check square error increase. Does that increase by more than 2 of these 2? If you reduce by delta k, but increase by delta at most delta k over 2, you get one forward, one backward, but you actually are better off than you're starting because you are decreased by at least epsilon k over 2. Therefore, the backward step makes sure when you go forward, go back to an earlier stage, you actually always improve your objective function. So you just repeat this guy and until you cannot do that. And you can show this term in polynomial time. That's always the case, polynomial in epsilon. Then you have a sparse recovery result signal. I'm just trying to give a very high level and compare to the earlier results with the not doing this. So again, this kind of similar in the setting of fully corrective. Fully corrective is here. No, not this one. Fully corrective is here. Results compare with that. This is k, sparsity k bar. This is result and using similar assumptions. But the other one, you get better in the sense of G. G is to say J actually should be larger. There seems to be a lot of typos. Here should be this one larger. The number of ambiguous, actually unambiguous features. Basically, J should be larger is small. Sorry about that. So and then if not only each it is sparse and this one, but also each component is relatively large. That's some small number. Then your error is in terms of this number. So this there is some typo here. It should be larger, and ambiguous should be unambiguous. And then you only instead of using k bar, this one can be no more than k bar, but you only in terms of the ambiguous. Actually, I missed it. Right. This is correct. Ambiguous feature is small. Basically means larger than that. Sorry, so I don't know why. The number of basically the set of small weights, small non-zero weights is small. Basically, a lot of weights are quite bounded away from 0. In this case, you only in terms of the small weights instead of so this one can be much smaller than k bar. And in that case, this algorithm will do better. So intuitive example for the feature selection, why you use less, you are more effective in the sense you will use less number of features to solve problem is the following case. In the forward, fully corrective forward, imagine this case, this example, I just, it's a simple example, F1, F2, your target is a linear combination of F1, F2. Then you also have F3, F4, F5. F3 is closest to Y, but it doesn't expand Y. Y is only expanded by F1, F2. If you just do forward greedy, you will pick F1, eventually pick correct. For example, you're starting with F1, F1, F3, F1, F2. In that case, you made a mistake in the sense you will add an actual feature which is not necessary. Because when you do the backward, once you F3, F1, F2, at this point, you will find that Y is already expanded by F1, F2. So you can actually remove F3 at this point. Therefore, you have a more compact model. And that turns out to give you better. This is where you hear this condition. Because you always, each time you have to judge whether weight is smaller. And this is get you a more compact model. I will quickly mention another optimization. It's a little bit more general than sparsity optimization. It's generalized sparsity constraint problem. The reason is this is a variables. Structure sparsity means you want to take correlation of the variables into condition, the neighborhood structure. Instead of these variables are completely unrelated, in wavelet, for example, you may say if this happens, this has to happen. You follow a tree structure, or follow neighborhood structure in a graph, for example. And in this kind of flavor, you want to introduce a different cost function than just merely the counting number of non-zeros. You put a more sophisticated function to say, I will encourage the if they are close together, if this kind of targets, this variable select the close together variable being selected together, then I will have a smaller penalty than if they are just randomly distributed. Here is given a support of W. You try to keep a cost function. This cost function will be smaller if they are close together. They will be larger if they are random, completely random. So you want to minimize this cost function. Here is a little bit the change of your greedy algorithm. Again, you want to each time you want to find each time instead of adding one component, you have to add a block set. You have to add a few components simultaneously. Then the key idea is instead of trying to say Q old minus Q new is large, you want to look at the new set you are forming by adding to the old set. Your complexity increases while your cost function decreases. You want to say per unit increase of your complexity, you want to reduce the cost function most. So this is the intuition. This is generalization of your greedy algorithm. Maximize decrease of objective function per unit increase of cost. Here is what you can say about that. Roughly, you have a fine W with complexity CW. CW is the complexity to compete with the target of S. So the idea, again, similar. Recall we have a similar formula. You want to find W such that which probably with CW larger than S, but you want to compete with the best possible with S. Here is S with a complexity S is what your optimal. And so what you can do is you say how much worse CW should be. Here is bound under some kind of restricted convexity. CW should be larger than S, but it's a logarithm in terms of 1 over epsilon. If you make more assumptions, you can say CW should be constantly larger than S. The interpretation is compete with complexity of S with a not much more complex solution. The solution W is a complex CW, which is ignore the log, you have constantly larger than S. So that's the that's kind of results. You can do local search and so on this type of things as well. But this is a basic generalization of totally corrective boosting. So using the structure. Here is the example. Just say when you do the structure, actually it helps. I'll show you an example because this one you introduce a new optimization procedure. The question is why you want to introduce new optimization procedure? Because you want to take advantage of this structure. And turns out when you take advantage of this structure, the performance increases. And this example just say this one is you don't take advantage of a structure. This is original image. This is using the greedy algorithm. This is using the convex relaxation. This one is actually when you really use the structure. And again, similarly, this is the case. So when you use a structure, turns out you can actually do better. That's why we want to put the structure on top of this sparsity. So you have to change the sparsity of optimization to become the structure sparsity optimization. Basically, in summary, so I want to just give a summary of what I talk about. It's talk about the greedy algorithm variations and their theoretical properties. One thing I started with is more classical, starting with the 50s, Frank-Wolf algorithm, which is L1 constrained greedy algorithm. The algorithm itself, the problem of if you want to implement this algorithm, it will depend on some kind of constraint size A and learning rate, which is not good. It's more practical. It's gradient boosting, which is a Friedman's algorithm, removing A dependence You don't need to worry about A, which is making it much easier, but it still depends on a learning rate, which is Friedman calls step size. Then once you can remove this eta, make it fully adaptive by using fully corrective boosting. Based on top of this Friedman's algorithm, you do a fully optimization with your convex set, within the active set of select features. This one get rid of this A and eta problem. Then on top of that, you can do local search. The local search will give you better feature selection, and in the set, you can do feature selection better. I'll give you one intuitive example, then you can actually get better results because you get a more compact solution. Then you don't do the local search results. You just do complete fully greedy, you get a less compact solution than you include backward step. That can help when you can do feature selection. Then talk about generalization. Generalization is to say instead of a sparsity constraint, you can do the more complex, the structured sparsity optimization. It's slightly more general optimization problem, so it's harder than the original problem. I talk about a specific algorithm. It's generalization of fully corrective greedy algorithm, but then you can do the other things. Similarly, you can study in this framework. Finally, I want to say a little bit about this sparsity optimization. Personally, I'm more interested in greedy algorithm and the local search simply because I think it's, at least for this type of problem, sparsity constraint is a more powerful algorithm. A lot of people actually more interested in the convex relaxation. I think the reason is probably it's easier to understand the convex relaxation in the sense of you just write down the formula. Convex relaxation is not a procedure, it's just the optimization problem. It changes the optimization problem. And the good advantage of that, you can use different procedures to solve that. Disadvantage is more, I don't know, it's you can argue it's less flexible in the sense greedy algorithm, you can have all the variations. It directly attack the underlying L0 problem more directly than L1. L1 is just 1. You cannot relax to L0.5 to call it convex relaxation. So you're basically stuck with this. And then you will think about optimization. This is not optimization procedure. It's just the formula. Once you look at optimization, a specific optimization procedure will be greedy-like. Therefore, this is called Lars, the solution. And if you look at this solution, then you can study this particular optimization procedure and expand that to look at other greedy algorithms, which are attacking the underlying problem more directly. Of course, the advantage of L1 is you don't have to use Lars, you can use other problem to solve. But then you have the limitations. You are essentially equivalent to a specific kind of greedy algorithm. So that's it.
So in your, I guess, the Frank Wolf type of algorithm, there's two flavors. One is the first, one of the formulations is minimize the components, EI,
right.
Also the eta simultaneous.
Right.
One of the formulation.
Right.
Second formulation, you have say, just fix some eta I, and then just find the best.
What is second? You mean it's L1 constraint or?
In the first one,
Let's look at that.
Go forward here. Backward, yeah, backward. Here.
Yeah.
This is backward one. Here.
Okay, right.
So here you have ij, eta j. So that's the minimization problem is simultaneous over the eta and also the ei.
Right.
Yeah. And the next slide is the next algorithm. In fact, here the difference.
You don't have A.
Yeah. You know in the algorithm, in the other means step.
Yeah. This actually is wrong. So I think I have some kind of you don't have A here also. So this one you should read. Yeah. I think I just copy paste. There are a lot of typos I noticed.
No, I mean the line above. The line above is you fix the eta j and then choose the best EI, right?
You can also optimize over that. This doesn't make too much difference because you can also pick specific eta j here as well.
Okay. Because you call it in the greedy boosting, essentially the algorithm is just first we find the best EI, and then you try to do a line search to find the eta J.
You can do, you can, the AdaBoost does that. Yes, you're right. But that's but AdaBoost would be equivalent to simultaneous finding I and J, I and eta.
Okay, my question. Okay,
it doesn't pick the step size. It's equivalent to optimizing simultaneously I and eta in this particular form. So that will give you AdaBoost, exactly the updated loop of AdaBoost.
Okay, that's simultaneous optimized. Okay. Yeah,
it is,
question.
yeah.
My question was just basically, it would be easy to first find the direction EI first, then do a line search for EJ for eta J.
You could, yeah, but Friedman does fix. You can do this version. This version basically, let me see the version of fully corrective. You can do the gradient, or we'll do it a different way. There are several different ways to find the I without using the step size. This is one way. There's another way. You make it the least squares problem. So there are seven. I didn't mention too much about that because I'll focus on the other things. But there are several. They are all okay. So here is to say you want to find the maximum gradient. There are different versions of all that. And then once you find that, you can say yes. You can pick the step size. You can replace this guy by finding the max gradient. It's okay. Yeah. And then you optimize. But that's still not fully corrective because you are only optimize eta. If you get fully corrective, you have to not only optimize eta, you have to optimize everything. Yeah. Yes, you can do that. Yeah. So I think that's good. Yeah. When I wrote that down, it's not the only version. There are variations. I think I didn't really go into that because I'm focusing on the other side of the story, not the variations of implementing greedy algorithm.
Just have a basic question. So if you go back to those compression pictures that we had,
Which?
The two images that you showed.
Oh, the images, the image recovery.
You're doing compression, right?
It's an image recovery. So you send out some random projection of this image. From the random projection, you want to recover the original image. It's kind of a compression.
And you're learning the random projection.
No, you don't. It's a random projection. It's just random projection. It's like.
So then you're just learning the mapping back to the original.
Yeah. You're learning back given the observed by compressed sensing, you random project that to a small set. Given that you go back.
So how is this? Is this the best method for doing this?
I think people talk about the structure sparsity a lot nowadays. So I don't know if it's best. There are also convex relaxation versions of that. There are other things. Of course, we want to say it's best, but I don't think that's not necessarily true. It's just one algorithm. The advantage of ours is we can prove things. Well, I don't see a lot of people doing that. They just give formulations and say it's good. That can show you a picture maybe like this, but they don't have this thing. So there are other versions. This is not only. So that's why I'm saying I'm not giving a comprehensive review of the literature. I'm just focusing on others.
There's kernel methods to do this too. There's kernel methods to do this exact problem.
That I don't know. So maybe this one is a little bit not quite related to kernel, but maybe it is.